Yes, I'm just gonna check my phone again.
Can you also explain why the fusion is called the process?
Why the helium fusion is called the triple alpha process? That's easy, because another name for a helium nucleus is an alpha particle, and 3 helium nuclei fuse to form the carbon, hence triple alpha process. They don't all 3 collide at once. 2 collide to form a beryllium-8 nucleus, which is very unstable, and so if another helium comes in just in time, they can fuse to form the carbon as well. Because 3 particles colliding at the same time is extremely rare, so that would never work. It has to be a 2-step process.
Would we have to know about that piece or?
No. But I'm sure you want to know. You'll remember just because you want to know so badly. Yes?
What's a planetary nebula and how is it formed and what causes it to glow?
Yep, so planetary nebula surrounds what kind of stellar remnant? Is it a white dwarf, a neutron star, or a black hole that it surrounds? Hint, the sun will someday form a planetary nebula. What's the sun going to leave behind? A white dwarf. So a planetary nebula, the name comes from early observers looking at them visually through telescopes. They thought they kind of looked like planets. Well, if you look at photographs of them, no, not really. But a planetary nebula surrounds a white dwarf, and I don't think I have a picture of one here in my slides, but there's a very famous one that you've probably seen pictures of before. So I'll just bring that up just by Google searching Ring Nebula. Here it is. You've probably seen this before. This is one of these things that you've seen photographs of even if you didn't know what it was. So this is the Ring Nebula, and in the middle of it here is the white dwarf. This is a low-mass star, similar to the sun. Remember that at the end of its life, the last thing that happens before you leave behind the white dwarf is there are helium shell flashes, sudden flare-ups in the rate of helium fusion in a shell surrounding the core that collectively push off the outer layers of the star. And that's what the planetary nebula represents. It's the outer layers of a low-mass star that were pushed off into space by helium shell flashes. The last flash does the most damage, so to speak. And it leaves behind the bare core. For a low-mass star, the bare core is made of the carbon from helium fusion. So you've got a dead stellar core made of carbon that is a white dwarf. The white dwarf, why, this thing was the core of a star. And so when they are born, they're very hot. Their surfaces are giving off lots of ultraviolet light, which ionizes the gas in the nebula. And then when electrons recombine with protons, they do the same thing that happens in an H2 region. You get photons because of electrons being captured into higher energy orbits and then dropping down towards the ground state. So ultraviolet light from the white dwarf ionizes the planetary nebula, and recombination radiation, electrons recombining with nuclei after being stripped off of them by ultraviolet photons from the white dwarf, is what is causing it to glow. They only live about 50,000 years, which is an eye blink astronomically. 50,000 years is forever in human terms, but in astronomical terms, 50,000 years is the blink of an eye. So they're very temporary phenomena because they're spreading away. After all, they were blown off the stars, the core, and so they're dissipating into the surrounding interstellar medium, and it takes a few tens of thousands of years for that to happen. They merge with the interstellar medium, and then that low-mass star has made its contribution to the next generation of stars in terms of adding some heavy elements into the interstellar medium that future stars can contain, and maybe planets. Yeah, we don't have a cute little cricket in here. Not crickets. They can see first. Yes.
So you have a question from chapter 18 that says to know what a gravitational redshift and a gravitational time dilation.
Yep, gravitational redshift and time dilation are two sides of the same coin, because gravitational redshift says that light emitted from deeper inside of a gravitational field gets redshifted as it climbs away from the star or the planet or whatever that it is on. So, in particular, for example, light coming off the surface of a white dwarf, we can actually measure that spectral lines are redshifted because of the gravitational field. Light loses energy as it climbs out of a gravitational field. An object like a ball slows down if you throw it higher. And that's how the ball loses energy. It loses kinetic energy, if you will. A photon can't slow down. It can only travel the speed of light. But it can lose energy another way by having its wavelength get longer. And so photons lose energy as they climb out of a gravitational field, and they do so by getting longer in wavelength. But if photons are getting longer in wavelength, then that also implies gravitational time dilation, because the idea would be, imagine that I have a light source emitting light, and so if I look from far away, I'll see that light is being redshifted. If I look back at the source of light from far away as it climbs out of that gravitational field, the light is redshifted. So if the wavelength is longer, what happens to the frequency? What happens to the rate at which waves are passing by me in terms of the number of wavelengths that pass by me every second? Longer wavelength means, is it higher or lower frequency? Lower frequency, lower frequency. Well, imagine that you set up a clock that ticked once every time a wave crest was emitted from the light source. This would be extremely fast ticking, but it's the principle that matters here. You have a light clock that ticks once every time a wave crest is emitted. What that implies is, if you're looking from far away, you're seeing fewer wave crests pass by you every second. You're seeing a redshift. But that would mean you would also see the clock ticking slower, because fewer ticks. The ticks would, the light from every tick, maybe it emits a pulse every time it ticks. Those pulses of light would follow the wave crests all the way up. So when you're looking at that clock from far away, you would see it ticking more slowly as a result of the gravitational redshift. Because if it's emitting a little light pulse every time it ticks, those light pulses are getting further away from one another as they climb out of the gravitational field. That's what the redshift means, is wavelengths or distances between pulses would increase. And so, in other words, gravitational time dilation refers to the fact that time passes more slowly in a gravitational field, that gravity slows down time. And gravitational time dilation and gravitational redshift are two sides of the same coin. If you have one, you must have the other, and vice versa. Yes? Solar thermostat, yeah, so like what would happen? So first of all, the solar thermostat is our friend, because it's why the sun does not explode like a bomb. And one thing that will really ruin your day is if your star explodes like a bomb. It sucks when that happens. So why not? Why does the sun not act like a bomb? I'm just going to start closing lots of these, and I'll just open again. I have to. Why doesn't the sun explode like a bomb? It's because there's negative feedback in the core. If conditions in the sun's core were such that it got a little hotter, very naturally it would cool back down again, and vice versa. And the argument goes like this. And I'm trying the sun, yeah, here it is, right, the sun chapter here. The solar thermostat prevents the sun from exploding like a bomb. So, for example, suppose that for whatever reason the core temperature rose, then nuclear reactions would go faster as a result of that, because if the nuclei are moving faster, they can more easily overcome their electrical repulsion, and so the nuclear reactions would increase. And if that happened, though, that would raise the pressure in the core, and the effect of it would be to make the core expand and cool back down again and return things to normal. So that's the idea with the thermostat, is that similar to the way a thermostat in a house is designed, right? In other words, if you've got a thermostat, and imagine you had this, generally thermostats only go one direction, but what if you had a thermostat and it was set that it would turn on the air conditioning when the temperature got above 72 degrees Fahrenheit, and it would turn on the heater whenever the temperature went below 70 degrees Fahrenheit. Then your house would stay between 70 and 72 degrees, because whenever it got above 72, it turns on the air conditioner, cools it back down again. And whenever it got below 70 degrees, it turns on the furnace and heats it back up again. And so it keeps things nice and steady. And the sun has something kind of like that. If the sun's core heats up, the result is that fusion reactions would heat up, make the core expand, cool back down again. Cool. So we go back to normal. If the core would have cooled down, fusion reactions would slow down, the pressure in the core would drop, the core would contract, convert gravitational energy into thermal energy, heat back up again, and we're back to normal again. So by analogy, it's not literally a thermostat, but it's like a thermostat, and then it keeps things nice and stable inside the sun. Nobody else is doing it? Is it, yeah?
And can you go over the Balmer thermometer, please?
So the Balmer thermometer is how we can, it's the explanation of why it is that, which chapter is that in? Is that 15?
Yeah.
Yeah. It's why it is that it describes the relationship between the strengths of a star's spectral lines for various elements and the star's temperature. So it's the great astronomer Cecilia Payne, later Cecilia Payne-Gaposchkin, when she married a Soviet astronomer, was the first person to understand this process. Did it when she was a grad student. That's pretty impressive. She did it for hydrogen, but we can make similar arguments for other elements. Question is, so hydrogen lines are darkest, most prominent. The absorption lines are darkest, most prominent in stars that have a surface temperature of around 10,000 Kelvin. They're weaker in both hotter and cooler stars. And at first, astronomers thought that that meant that stars, A-type stars, A-spectral class stars, which are the spectral type that this corresponds to, had more hydrogen than other stars, and that's why they had stronger spectral lines. But what Cecilia Payne showed is that's not it. It's the temperature. All stars are made mostly of hydrogen and helium. It's the temperature that determines how strong the hydrogen spectral lines are, not how much hydrogen there is, because all stars have about the same percentage of hydrogen in them, namely about 9 out of every 10 atoms in a star is hydrogen, about 75% by mass. And remember, we told the story of Goldilocks and the 3 stars. Goldilocks wanted to find a star with nice, strong hydrogen spectral lines. So first she went to a star with a temperature on its surface of much more than 10,000 Kelvin. But that star was too hot. It was so hot that violent collisions between the hydrogens, between the particles, meant you couldn't even form hydrogen atoms because it would strip off the electrons. There's no way an electron could stay attached to a proton and be a hydrogen atom in a star like that near its surface. If there's no electron orbiting the nucleus, there's no way to make spectral lines. And so those stars have weak hydrogen spectral lines because there's very little atomic hydrogen in them. It's almost all ionized. And then she went to a star with a surface temperature of much less than 10,000 Kelvin, and that star was too cool. It was so cool that collisions were not very strong between atoms, and most of the atoms had the electron in the ground state orbital. And in the ground state, you don't form the visible spectral lines of hydrogen. You have to be in the n=2 state, the first excited state, in order to form Balmer series visible spectral lines. Because if you're in the ground state, it takes ultraviolet energies to be absorbed to move up to higher energy levels. So if you want to see visible hydrogen spectral lines, you don't want atoms that are in the ground state. You want atoms that start with their electron in n=2. And in a star with less than 10,000 Kelvin temperature, there's very, very tiny fraction that have n=2, and so as a result, you have weak spectral lines because there's very few hydrogen atoms where the electron's in the n=2 level, the first excited level. At 10,000 Kelvin, you get the best compromise where collisions are strong enough to put a reasonable number. Most of them are still, it turns out, in the ground state, but strong enough to maximize the tiny number, it still turns out, that are in the n=2 state, but not so strong that they ionize it. And so Goldilocks said, oh, this star is just right. It has the right temperature to give the strongest hydrogen lines. And that's the Balmer thermometer. The strength of the Balmer series visible spectral lines is correlated with the surface temperature of the star. Yes?
So correct me if I'm wrong, but iron can't fuse with itself, which is why it's a bad thing if the core is fully made of iron.
Yeah, so you were basically right. The only thing I would change is you said iron can't fuse with itself, but we can go further than that. Iron can't fuse with anything. Yeah. Or it can, but it takes energy to make it happen. You have to force iron to fuse with something else, and you have to put in energy. It's endothermic instead of exothermic in the way that you might hear about in a chemistry class. So it can't serve as a nuclear fuel for a star because it doesn't give off energy when it fuses, it sucks in energy when it fuses. And so you can't use it to power the star. And so the star is doomed when it's got an iron core because now it cannot have another set of nuclear fusion reactions that can keep helping support the core from collapsing. And so that's why iron is, when it forms the iron core, that's the beginning of the end for a high mass star. The end comes quickly. It's like if once the iron core forms, you're like less than a day from the star blowing up as a supernova. So we don't know what, when we're seeing Betelgeuse as it was like 500 years ago, we don't know if tonight we'll be seeing it when it has an iron core, in which case, if it is, oh, it's going to do what I keep asking it to do, blow up. But we have no idea what it's doing, because you can't tell from the outside what a high mass star is doing from the inside the way you can with a low mass star. I'm guessing my battery's getting low, but it should still have some juice. Turns out shooting video for over an hour is very battery draining. this though, because boy, there's nothing worse than watching yourself on a video. We're all our own worst critic. You know, I've seen like Hollywood stars that say, I never watch my movies because I just can't bear to, you know. So I'm not saying I'm a Hollywood star, but anyway, yes.
The last question for chapter 15, it said, understand how the age of a star cluster is determined from the location of the turnoff point.
Yeah, that's something that we did talk about earlier, the
Okay.
turnoff point, yes. That's early on, so watch the video later. Yes,
Why was the Hubble Space Telescope placed in orbit?
to get it closer to the stars. No, right, I'm glad you shook your head, yeah, no, right, I'm making myself cry. Right, right. So the biggest reason to put it into orbit was to get it above Earth's atmosphere. Because Earth's atmosphere blurs things, right? Atmospheric turbulence blurs images. Also, you can observe at infrared wavelengths that are absorbed by our atmosphere using Hubble. You can observe at ultraviolet wavelengths that are absorbed by our atmosphere using Hubble. But that's what it comes down to, is, you know, why spend all that money getting a telescope which would not be among the world's largest telescopes if it was on the ground. It's big, but it's certainly not. On the ground, it would not be a world-class telescope. But in space it is, because it's above the atmosphere, so that it can make images that are as sharp as the diffraction limit will allow. It reaches its theoretical angular resolution because it is above Earth's atmosphere. And then, you know, there's other things like you never have to worry about daytime in space because you just don't point it in the sun's direction, you know, so. I mean, if you wanted to destroy it, they could point it at the sun, but it turns out they don't want to do that, so. Stephanie, yes.
Can you go over uniform circular motion?
Yeah, so uniform circular motion means motion in a circle at constant speed. So uniform means at constant speed. So here I am doing my best approximation to walking in uniform circular motion. My speed is constant. Am I accelerating?
Yes.
Yes, because while my speed is constant, the what is changing? Direction I'm moving is changing, yep. So uniform circular motion, there is acceleration, and the way I have people figure out which way the acceleration is pointing is to say, well, remember that the force points in the same direction as the acceleration it causes. So I always like to imagine, because I used to do this, pick up little sister, swing her around, okay? Don't let go, because then she'll run to mom. I speak from experience, okay? So in order to keep her orbiting around me, do I have to push out or pull in? I have to pull in. I'll be pulling in. The faster I go, the harder I'll have to be pulling in to keep her from flying away. And so that says that the acceleration is towards the center. The required force is towards the center. It's a centripetal force, a centripetal acceleration. And it helps us understand orbits. Orbits are generally elliptical, but the simplest case would be a circular orbit. And in that case, say you got a planet going around the sun. Okay, the sun doesn't have arms that are holding the planet in, putting a force towards the center. But what does the sun have that keeps it's gravity, yeah. So the force of gravity plays the role of your arms holding in little sister. When a planet holds a planet when a planet is held in orbit by the sun's gravity, or a satellite is held in orbit by Earth's gravity, or whatnot. Decided for plain chicken. If I leave, somebody might ask that one question that I really needed to hear. Or if I leave when I'm walking away, I'll think, I should have asked him that. Yes.
What are the characteristic sizes of the sheets and voids?
Yeah, so it's really the voids that we're looking at for characteristic sizes, and they're like 100 million light years across, roughly speaking. And the superclusters and sheets and all that, they're around the edges of the voids. Several 100 million light years across is what we're talking about, basically.
Can you go over the inflatory hypothesis?
Inflation. No, the inflationary hypothesis.
Inflationary, I'm sorry.
Inflationary hypothesis, yes.
Inflationary.
Sounds like we're doing economics, but we're not. So the idea is, remember when we looked in the very early universe, and we go through that timeline business, that notice that, right, and it's not known for sure what caused inflation. There's lots of ways to make theoretical models that would produce inflation. One idea, and it's not definitely right by any means, but the time that it happened is what we think is about right. So universe is 10 to the minus 38 seconds old, and the gut era is ending, and the electroweak era is beginning. The gut force split into the strong electroweak force. Notice it said, perhaps accompanied by a dramatic instant of expansion called inflation. And the idea is, in a tiny fraction of a second, something like 10 to the minus 34th power seconds, or 10 to the minus 32nd power seconds, some extremely tiny amount of time, the idea is that there was a dark energy present, a form of dark energy, much more powerful than the dark energy that's making the universe accelerate today. And the idea would be that the scale factor, the size of the universe, becomes very rapidly larger during that tiny fraction of a second. That the size of the universe would increase by something like 10 to the 50th power, 1 followed by 50 zeros, an unbelievably incredible expansion. That's what we call inflation. That the size of the universe dramatically and fantastically increased in a tiny fraction of a second shortly after the Big Bang. Due to some form of dark energy which is different from the dark energy that appears to be present in the universe today, a much more energetic dark energy than is present in the universe today. And it allows us to understand certain mysteries about the universe, including, and I think I've got that on the prior chapter, yeah, including, as we mentioned in class, the fact that the cosmic microwave background is so close to being the same temperature in every direction. Because without inflation, we would expect the cosmic microwave background coming from parts of the sky that are only more than about a degree from one another to be from regions that would never have interacted after the Big Bang up to the time when the universe was 380,000 years old. So there'd be no reason for them to be at the same temperature. But if you include inflation, what that means is that, in fact, the universe was much, much smaller earlier on than it would have been without inflation. And those two patches would have been close enough to one another to have come to the same temperature before inflation. And then inflation rapidly carries them much further away from one another, such that after that they stopped exchanging energy with one another, but they became at the same temperature before that happened, so we see them at the same temperature today. And inflation would also take what could be an originally highly curved, chaotic-looking universe and stretch it out so that the part of the universe that we're in is a tiny part of that original, very chaotic, highly curved universe. And if you get close enough to any highly curved surface, and that's even in hyperdimensions, this is like one of these two-dimensional analogies, but no matter how curved the surface is, as long as it doesn't have points on it, as long as it doesn't have like pinpoints on it, like the tip of a cone, if you get close enough, it looks flat, just like the Earth looks flat if you're close enough, leading some people to come up with silly flat Earth theories and so on and so forth, when it's really a sphere that's just being observed close up by us. And similarly, the universe would be as flat, our part of the universe would naturally look as flat as it does if there was inflation, because our part of the universe would have grown from such a tiny part of the universe before inflation that even though the universe as a whole was really curved, our tiny little part of it before inflation was practically flat, because a small enough part of any curved manifold, it's called, looks flat if you're in a small enough region of it. So. You okay? My knee kind of empathetically hurts right now because I look like one of those. Too bad I'm not gonna have time to edit the dead space out of the video. But I am gonna point out that you can watch YouTube videos sped up without it sounding like a chipmunk, because if you go to the preferences, you can tell it to play back faster, and they digitally process it so that the voice still keeps the same pitch, so that you can shorten the amount of time it takes to watch it. Of course, you might have to slow down if it's some complicated explanation and it's going by very fast. Once I was doing in my astrophysics class, I was drawing this dashed line to represent the surface. And then I played the video back fast. It was just somehow hilarious because it made me seem like I was a woodpecker, because it was more like, so it was very entertaining.
What is the protostar's source of energy?
Gravitational contraction. It's turning gravitational energy into thermal energy and radiation. Unlike a fully fledged star, which shines via what powers a fully fledged star? An adult star is powered by nuclear fusion. Yep. Yep. As a protostar collapses, its core gets hotter and hotter as gravitational energy keeps getting converted into thermal energy and radiation. Eventually the core gets hot enough for hydrogen fusion to start, and then you have, oh, congratulations, it's a newborn baby star. Well, or a newborn adult star, if you will. They just go from baby to adult, just like that. It's an interesting expression. The hell is this? It's okay, the phone's turned towards me. I won't mention who's making the funny expression. But maybe I could cure what's aching her, you know? But don't worry, nobody's gonna be watching by this point anyway. I always look at the number of views. It's like the first one, 21, the second one, 6, the third one, 2 or whatever, and it really starts dropping.